Here we made it to the last talk for today. It's actually the longest session in the program. So next up is Shijie Geng. Again, I hope I'm saying that right. A title with two acronyms: recommendations as language processing, and a unified pre-train, personalized prompt and predict paradigm. Floor. You have the button here, the green button.
This one?
Yeah.
Okay. Okay. Great. Okay. Hello, everyone. My name is Shijie Geng from Rutgers University. Today, I will present our paper, Recommendation as Language Processing, RLP, Unified Pretrain, Personalized Prompt, and Predict Paradigm P5. Let's first review the development trend of recommender systems. In retrospect of the past decades, we can summarize the development trend of recommender system as we want a more comprehensive system that accommodates first the more diverse features from traditional feature engineering to richer contextual features to with the development of RLP technologies, we can directly represent raw data with RLP techniques. And also, the recommender systems include a wider spectrum of application scenarios, from the basic applications such as the CTR prediction, rating prediction, and matching-based recommendation. Now, the recommender system has more applications in different topics. And also, the model size is gradually increased from the shallow model to deep model. Now, transfer to large models. So our motivation is, though the previous methods or approaches are achieving great success, the current recommended system still needs to design specific model architectures and the training objectives for different recommendation tasks. Since recommendation tasks usually, they share a common user item pool, and they have overlapping contextual features. So it's promising that we merge all these recommendation tasks into a unified framework that they can implicitly transfer knowledge to each other and benefit each other better. Consider that language is a powerful medium to describe both the problems and tasks, and also we can represent the raw data which reach our natural language format. We believe that the language model is a good candidate to build such a unified framework for recommender systems, and can enable that the recommendation model have a better generalization ability. There are some challenges to build such a unified framework. First is how to convert our data, such as the user item interactions, item metadata, user reviews, and different task descriptions into a common format that is a natural language sequence. We will introduce how we do this later. And we got inspirations from the recent advances in multitask prompt-based training with large language models. We got inspirations from the three works: T0, FLAN, and XT5. They both train multitask prompt-based model with large language models. But they focus on pure NLP tasks, and this task has nothing to do with personalization and recommendation. So that's why we build such a unified framework for recommender systems. Our P5 learns multiple recommendation-related tasks together through a unified sequence-to-sequence framework. It formulates different problems as prompt-based natural language tasks. And here is an illustration of the P5 framework. And the user item information and the corresponding features are integrated with the personalized prompt templates as the model inputs. The main advantage of P5 is that the models is immersed into a full language environment because language has its flexibility and expression ability. This is very powerful. So there's no need that we design feature-specific encoders. If I would treat our personalized tasks as a conditional text generation problem, so we made it one data format, one model, and one loss for all the recommendation tasks. And because language has the ability to conduct zero-shot tasks, so P5 attains sufficient zero-shot performance when generalized to novel personalized prompts and unseen items in other domains. Here is the 5 challenges we need to solve to build P5. First is what tasks are covered by P5. And second is how to represent user preference and item features in P5. The third is how to design personalized prompts for different tasks. And next is what architectures to use as backbone for P5, and how to conduct training and inference. Here are, in P5 paper, we cover 5 different task families. That is rating prediction, sequential recommendation, explanation generation, review-related tasks, and direct recommendation. But P5 is not limited to these 5 task families. It can be easily and flexible extend to new tasks with designed personalized prompts. Second is how to represent personalization in prompts. We give a definition of personalized prompts. It's a prompt that includes personalized fields for different user and items. For user and items, they both have two ways to represent the personalization. For user, we represent it as a string, include the user ID number, such as user underscore 23. And also we can represent the user with a description of it, of the user, such as the user's name, gender, and age, and so on. And for item, we can also represent it as item underscore 7391, and also item, a detailed descriptions of the item. Next step is to design the personalized prompt templates. We first divide all 5 task families in the raw data of them into 3 groups. Because rating, review, and explanation share one group of raw data, and sequential recommendation and direct recommendation have their own raw data. And based on each task family, we design various personalized prompts for them. Because for each task family, we need to design many prompts for them because it can help P5 to get better generalization ability. So finally, we create 47 personalized prompts to cover the 5 task families, and the details prompt list is offered in our paper. And after design the prompts in the left, in the right, and we have already provide the metadata in the left. So we merge them together. We construct the training prompts from personalized prompts templates by simply filling the raw data into the templates. Thus, we can build such input-output pairs. The left is the input, and the right part is the output, the expected outputs. So here is the architecture of P5. P5 is built on top of the Pretrain T5 checkpoints because we have to enable P5 the basic ability for language understanding. So P5 is in fact a sequence-to-sequence model. By default, we use multiple sub-word units to represent personalized fields. For example, the item underscore 7391 is divided into 4 sub-word units. Why we use the sub-word units is to increase the utility of each sub-word units. To help the model understand that the 4 sub-word units are from one complete field, we outlined the whole word embedding in P5. That's the purple ones in the figure. Based on the P5 architecture, like other text-to-text model, the encoder takes the input sequence, and the decoder auto-regressively generates next words. So these tasks share one auto-regressive language model loss. And as a result, it's one model, one loss, and one data format for all the tasks. When doing inference, different tasks have different strategies. For rating, explanation, and review tasks, we simply use the greedy decoding to generate the answer. And for sequential recommendation and direct recommendation, we need to have a list and then conduct an evaluation. So we use beam search to generate the list for both sequential recommendation and direct recommendation. Then we conduct some experiments to answer 2 research questions. First is, how does our model, our P5 framework perform compared with the task-specific methods of all 5 task families? And the second is about P5's zero-shot generalization ability when transferred to unseen prompts or for existing or new items. We conduct experiments of P5 on all these 5 tasks. And here, because we designed some personalized prompts, there are some seen prompts that used for training and some unseen prompts just for evaluation. And the purple ones are seen prompts, and the orange ones are unseen prompts. Based on these results, we can have a conclusion that P5 can achieve promising performance on these 5 task families when taking seen prompts templates as the model inputs. And when we transfer to unseen personalized prompts, the orange ones, we can see that P5 can get enough robustness and to understand the prompts it never saw before, even with some wording variations. And we also trying to transfer P5 to items in new domain. Thus, we design some zero-shot prompts. Just give some facts for a new product and ask the model to do something, whether to predict whether the user like or dislike it, or generate explanation for the user for the item. Sorry, and we gather some user that exist in all these three data sets, and we conduct some zero-shot transfer. And the conclusion is that P5 still maintains sufficient performance for most tasks, such as rating prediction, like-dislike prediction, as well as the explanation generation with feature word. And here is an example that there are examples that when we transfer we train a model in one domain and transfer to another domain, and P5 can still generate plausible explanations. So here are the conclusions. P5 unifies different tasks into recombination tasks into a shared language modeling and the natural language generation framework. And we provide a list of personalized prompts, and it covers 5 task families, and our raw data are transferred into the same format. And P5 beats or achieve similar performance with several task-specific representative approach, and it shows generalization ability on performing zero-shot transfer to new items, new domains, and new personalized prompts. In the future, P5 can be further extended to more diverse modalities and more personalized tasks. And we can even build more large models for P5. Thanks for listening.
Thank you very much for the presentation.
Thank you.
We were already past the Q&A time as well.
Yeah.
So I'm going to ask you to, if you want to answer the questions on the RecSys website. But yeah, thanks for the presentation. Thanks everyone for being here. This was the last talk for the session. We hope to see you again tomorrow at 9. And please thank all the speakers once more.